Okay, good morning. So I want to start from page 65 and a little before page 65 I have, let me see, think, here. So the question is what is the eigenvalue of V inverse? You know, what is see you have some V inverse and you have eigenvector. Is it lambda gamma 1 over lambda gamma and gamma? So this is a question. Because what we have is Vn. This is for sure we have Vn gamma equal lambda gamma and gamma. Yeah. So I think what we should do is we multiply V inverse here and here too. V inverse. So we have n to gamma equal lambda gamma V inverse n gamma. So we have this V inverse n gamma equal 1 over delta 1 over lambda 1 over lambda gamma n gamma. Yeah. So that means this is correct. This is correct. Correct. G. We can use the Cayley-Hamilton theorem, which states that any square matrix satisfies its own characteristic equation. To obtain the square root of matrix, the characteristic equation for G is equation 572. Yeah. So this is the Cayley-Hamilton theorem. According to Cayley-Hamilton theorem, the matrix G satisfies. Let me check my mic condition. Mic condition is okay. The matrix G satisfies the matrix polynomial equation. Let's go back to 572. 572, we have this one. Okay, so this is the eigenvalue. Eigenvalue satisfy this equation. The matrix you just replace eigenvalue with matrix itself. Okay, then you get Cayley theorem equation. So this is eigenvalue. These are eigenvalues. And this is the original matrix where O is 3 by 3 matrix with O element 0. We have also used the notation P for matrix function obtained from the regular function P. This result implies that any power of G higher than 2 can be expressed in terms of G squared, G, and I. In fact, any matrix function phi of G can be expressed the same way. Moreover, the eigenvectors of G are also eigenvectors of phi, and eigenvalues of phi of G are small phi of G. Eigenvalues of matrix phi of G are phi of G. Any matrix function can be expressed in the same way. So G to the power 1/2 is A G squared plus BG plus CI, where the coefficient ABC has to be found. Okay. For three eigenvalues G gamma of G, the eigenvalues of G 1/2 and G are eigenvalues G to the power 1/2. Using these, we get three equations. G eigenvalue G gamma to the power 1/2 equal A G squared BG plus C, where gamma is 1 to 3 for A, B, and C. When there are repeated roots G gamma, we may use the Frobenius method in which we form a new equation for ABC by differentiating equation. New equation for ABC by differentiating. With respect to G. Do you get that? I'm not very sure. Differentiating G. Frobenius. We substitute these coefficients to equation 2 130 to get C to the 1/2. We may anticipate complications when the eigenvalues are not distinct. If lambda 2 equals lambda 1, we follow the Frobenius limiting process. We begin by assuming lambda 2 equals lambda 1 plus epsilon, then one of the three equations for Ci becomes like this. If we subtract the equation corresponding to lambda 1 and divide by epsilon, we have something like as epsilon goes to 0, we obtain the needed additional equation. That's a Frobenius method. So okay, if we need like three values. If we need G1, G2, G3, I mean three values. From these three values, we can obtain A, B, C. But if, for example, G1 happen to be G2, you only have two values. So you can have you have two equations. For this, you only have two equations. Yeah. Then what you do is you differentiate. So that means you go like G gamma and to the power minus 1/2, 1 over 2 in front, equal to G gamma A plus B. So this one, you can use this equation as the third equation. This will be the third equation. So then you can obtain ABC. Okay, I think this is clear. And 5, 3, 8. Example, polar decomposition. Okay, consider the formation of a square region in the x1, x2 plane. First, let us stretch this region in the x1 direction, doubling the length. Okay. Then we rotate it by theta equal 30 degrees. The spatial coordinates of initial point x1, x2 become this is a little bit strange. Maybe okay. So you just stretch. There is a figure, right? Okay, let's see. Here you stretch, then rotate. Okay, so the Green's deformation gradient matrix is obtained as, see, let's do this. This cosine theta. What is cosine theta? cosine theta is like this. Square root 3 over divided by 3, 2. That's a cosine theta. Sine theta. Sine theta is 1/2. So you have here, you have square root of 3, square root of 3, and this is 1/2. 1/2. 1/2, right? And f goes like alpha I think. So this is the partial alpha, partial Green's deformation. This one. This is alpha xi. You go small xy. Small xy. Yeah. So partial x1, partial large x1, that's this. And partial small x1, partial large x2, is this. So which goes here. It's kind of stretch. Yeah. Okay. So then I have found a mistake. This one is actually 1/2. And this guy is square root of 3/2. Yeah. So now you can this guy go here. So then you have this one is partial x2, partial x1. Let's see, alpha I. This is partial x2. Partial x2, partial large x1. Yeah, because you have alpha I. 1, 2, 1, 2. Then you get this 1. So this one is partial small x2, partial large x2, which is this. Okay. So the green deformation matrix is obtained as G equal FF transpose square root of 3, 1 minus 1 half, square root of 3, 1 half, and transpose is square root of 3, square root of 3 divided by 2, 1 minus 1 half. So this is like 4, 1 half, 0, 0, yeah, and the square root of 1/4, 1, 4001. The characteristic equation for G is found as this, so the eigenvalues are G equal 4 and G2 equal 1. The corresponding eigenvectors are 1, 0, 0, 1. The spatial ellipsoid for this plane, deformation, plane deformation is given by this. Where we have assumed the radius of spatial sphere k equal 1. Interesting. Spatial ellipse. Yeah, I think we have this. G. I think it was like this. K square equal 1 equal dxi dxi. Okay, this is just a sphere, which is equal G alpha beta d large X alpha d large X beta, right? So then alpha go 1, 2, 3. So this is, you just have G entry you have is G11, yes, which is d X alpha square. Another entry you have is G22. So excuse me, that means G dx beta square. That is 4 dx alpha square plus dx beta square. Yeah, so this is 0.5 dx alpha square plus 1 dx2 square. This equation. Okay. Well, we have assumed that the radius of the special sphere is k equal 1. The square root of the diagonal matrix G is B 2001, and using this we obtain R equal this. So is it RB or BR? RB or BR? BR. Let me see. BR. G. I think this textbook should show this definition every time. The square root of G is, this is okay. Okay. And how do you obtain this? Using this, we obtain this. F is VR. F equal VR. So F V inverse F is R. So what is V inverse? This is 1/2 001. And then F, what was F? Square root 3, 1, 1/2, square root 2. On half square root 3, 2. Is it correct? Was there a minus sign? Minus 1, 2. This is minus. So you can calculate. This is see, this equal square root of 3 over 2, 1, 1/2 minus 1/2 square root of 3 over 2. Yeah, so we got this. This corresponds to the 30-degree rotation we imparted to our region. inverting the matrix F, we get this is F, this is F. So we make inversion. That means 3 over 4, 3 over 2 plus 1 over 2. Then you have inversion here. Square root minus 1 half. So the 1 half. This part is 1 half. So you have 4, 2, 4, 2. Okay? So this is small f. And g, small g is FF transpose. FF transpose. So this is F. And what is F transpose? It's the square root of 3, 4, square root of 3, 4, 1 over 4, minus 1 over 2. And you get this factor out, so you don't have 4, 4 anymore. Times 2, times 2. You don't have 4, 4. This is 2. You don't have 4, 4 anymore. Here, just multiply 2, multiply by 2. So what do you get? 7. So you do like this. Square 3 minus 2, 1, 2 square root of 3, square root of 3, square root of 3 divided by 2, 1 minus 2. Okay, you have 7 here. Then you have 1. This is strange. This is 2 square root of 3. This way. Okay, 1, 4 minus 3. Okay, this is okay. This is okay. Okay, this is okay. So this is okay. eigenvalue of g, small g, is 1 over lambda 1 square equal 1/4, and lambda 1 over lambda 2 square, which is 1, and the corresponding principal directions are you have to calculate this one. You have to obtain, this is a kind of interesting, strange. So if you have, in this case, okay, let me skip this calculation here. Okay, please try this exercise by yourself. Then let me try doing let me try this a little bit. So now you had yeah, you have spatial, this is material, this is material space. Then you have spatial, actually material coordinate and spatial coordinate, right? So you had a sphere here, radius k equals 0, k equals 1. So then what you had is 0.51. So this is the ellipsoid, right? So this is the ellipse. So here you have dx I dxi equal 1. So this is mapped to this 0.5 dx1 square plus what was that? 1 over dx2 square. So this is what excuse me. Yeah, because we stretch, we stretch and rotate, right? So this is okay. But the funny thing is, if we have small sphere here like this, so now you have dxi equal 1. Then this will get mapped to this strange which has semi-major axis of 2 and semi-minor axis of 1. What is that? This means length, and this means length. Yeah, then we have this one. Actually, this is like this way. This is 30 degrees. This axis. Then this guy, if you have 1/2 this guy, this way. And this is like this is 1, 2. No, I think this is like this. Semi-major axis of 2. So this is a major. This is semi-major. And this is semi-minor axis. So this is a semi-minor axis. So what you have here is, see, there is some direction like this. This is 1. This is 1. And this is 2. Then the angle here is 30 degree. Angle here or angle here is 30 degree. But then there is a semi-major axis of 2. So this way, your ellipsoid become like this. It's interesting, right? Uh, think okay. I think it's okay. What time is it now? 7:22. Example of square root of matrix. Consider the deformation gradient matrix, something like this. The Green's deformation matrix is obtained as this F times F transpose. The eigenvalues are obtained from this. Is it from Cayley-Hamilton? Which has a root. By writing this way, we found the equation for A, B, and C. Solution of these equations are these. Using these, we found V equal G1 half. Let me see how this is. You have A, B, C solution, so you have V. So the rotation matrix R and the left stretch matrix you have found as R equal V inverse F is something like this. U is R transpose F. Something like this. Of course, it is easy to see in the preceding calculation that we dealt with only a 2 by 2 submatrix. Can we use this 2 by 2 submatrix? Okay, if we use, because the third axis doesn't change anything. Third axis, but here you have square root. This is just 1. So this multiplies. So third axis is always 1. Okay, this multiplied by this is 1. Logarithmic strain. Apart from the Green's and Almarin C strain tensor, a third strain measure frequently used is the logarithmic strain. If we consider a bar of current length, what is current length? L, stretched by delta L, the incremental strain is delta e to power L equal L delta L divided by L, which was the infinitesimal form dE equal dL over L. Integrating this, we find when the length has changed from L0 to L, EL equal logarithmic L over L0, L0, using the left stretch tensor V, we have the tensor version of this relation. Okay. I let me skip this part. I'm not pretty sure what is the physical meaning only from this simple hand waving interaction. We don't understand, so I don't know if there will be more explanation later or something. But let me stop it here today. So we will continue from 5.5 change of volume next time. So this one we try next time. Next time we do